On the evening of April 13th, 2029, a moving point of light will cross the sky over Europe and Africa, slow and steady, bright enough to see with your eyes alone. It is a rock about the length of a cruise ship named Apophis, and it will pass closer to you than the communication satellites that carry your phone calls. The date has been known for years. Astronomers have ruled out any chance that it strikes us. What unsettles the people who track these things is everything standing around that one calm fact. Apophis was found in 2004, which gave us 25 years of warning for a stone that briefly looked like it might arrive. The rock that shattered windows over Chelyabinsk gave no warning at all, because it came out of the glare of the sun. Tonight we follow the whole story, from a faint dot on a screen to the watch we keep now. Set a date in your mind. The 13th of April, in the year 2029. It falls on a Friday, which is the kind of small coincidence that people will make more of than it deserves. That evening, if you're standing somewhere in Europe, or in Africa, or across the western edge of Asia, and the sky above you happens to be clear, you will be able to look up and watch an asteroid go by. Not through a telescope, not on a screen with a countdown clock in the corner, with your eyes, the way you would notice a star you had not seen before. It will not look dramatic. That is the first thing worth saying plainly. There will be no streak of fire, no glowing tail, no sound. What you will see is a modest point of light, roughly as bright as the middling stars that make up the Big Dipper, sliding steadily across the constellations. It will move fast enough that you can watch it move. Stand still, pick a star, and within a minute or two the point will have visibly changed its position against that star. In under an hour it will cross most of the sky from one horizon toward the other, and then it will be gone. The object making that light is called Apophis. It is a stone, roughly 340 meters across on average, with its long axis stretching to something closer to 450. If you set it down in a harbour, it would be about the length of a large cruise ship, and taller than most buildings in most cities on Earth. It weighs somewhere in the neighbourhood of 60 million tons, though that number is one of the things we are least sure about, and we will come back to why that matters more than almost anything else in this story. Here is the part that stops people. When Apophis reaches its closest point, it will be about 31,600 kilometres above the surface of the Earth. The satellites that carry television signals and weather images and a good portion of the world's phone traffic sit in a ring roughly 35,700 kilometres up. Apophis will pass inside that ring. For a short stretch of that April evening, a mountain of rock left over from the birth of the solar system will be closer to you than the machines humanity built and parked overhead, and nothing will happen. That is the second thing worth saying plainly, and saying early, because the internet has spent 20 years saying otherwise. Astronomers have ruled out any chance that Apophis strikes the Earth in 2029. They have ruled it out for the century that follows. The prediction is not a hope or an average. The position of Apophis on that evening is known to within a few kilometres, from measurements gathered over 2 decades, and the people who made those measurements are not nervous about them. What they are quietly uneasy about is something else entirely, and it sits just underneath this whole story. If you want to follow that thread with me, all the way down, subscribing is the simplest way to keep these long nights of space coming to you. Because the appointment on the 13th of April is not really the point. The point is how we got the appointment. Apophis was discovered in 2004. 25 years of notice for a stone that briefly looked as though it might arrive. That warning did not fall out of the sky. Someone had to find it on a summer night in Arizona when nobody was looking for anything in particular. The 19th of June, 2004, was an ordinary night on Kitt Peak. The mountain sits southwest of Tucson in the Sonoran Desert, and its domes stand in a scatter along a ridge that holds the dry, still air that astronomers want. 3 men were using a telescope there that night. Roy Tucker, an instrument maker and amateur observer of unusual talent. David Tholen, a planetary astronomer from the University of Hawaii. Fabrizio Bernardi, an Italian researcher working with him. They were not hunting for a dangerous asteroid. They were testing an idea about how to search the part of the sky that lies toward the Sun, where objects on Earth-crossing orbits tend to hide. The way you find an asteroid has not changed much in 130 years, only the tools. You take a picture of a patch of sky. You wait. You take another picture of the same patch. Then you compare them. The stars stay put. Anything that has shifted between exposures is close to home, and moving, and therefore interesting. In 2004, the comparison was done by computer rather than by eye, but the logic was the same one Max Wolf used with photographic plates in the 1890s. On that night, and again the following night, a faint dot shifted. It was very faint, near the limit of what the telescope could pull out of the sky background, and it was moving at a rate that meant it was somewhere in the neighbourhood of the Earth, rather than out in the main asteroid belt. The three observers reported the position measurements to the Minor Planet Center in Cambridge, Massachusetts, which is the clearinghouse where every asteroid observation on the planet goes to be catalogued. The object received a provisional designation, the way every new object does, 2004 MN4. That string encodes the year of discovery and the half-month within it, and nothing else. It carries no meaning and no warning. Then the sky closed. The moon brightened, the weather turned, and after 2 nights of tracking, the object was lost. 2 nights is almost nothing. From 2 nights of measurements, you can sketch a rough path, the way you can guess where a car is heading from 2 frames of security footage, but you cannot say where it will be next year or in 25. This is worth sitting with. The most closely studied near-Earth asteroid in human history was seen for 2 nights, and then vanished. And for 6 months nobody on Earth knew where it was. Not because anyone was careless, because a rock a few hundred meters wide, far from the Sun, reflecting a modest fraction of the light that lands on it, is one of the dimmest things in the sky, and the sky's enormous, and telescopes look at one small piece of it at a time. In the ordinary run of things, that would have been the end of it. Thousands of asteroids are spotted, lost, and quietly written off in the records every year. Most of them are small, and most of them never come back into view, and the loss cost us nothing but a line in a database. Apophis came back. Half a world away, in the second half of December, an observer in New South Wales pointed a telescope at a patch of the southern sky and found it again. His name was Gordon Garrard. He worked at Siding Spring Observatory in Australia, on a mountain in the middle of the New South Wales bush, and on the 18th of December 2004, he recorded a faint moving object that turned out to be the same rock that Tucker and Tholen and Bernardi had seen in June. Nobody realised it immediately. Garrard's observation went in as a new detection. It was only when the Minor Planet Center's software matched the new positions against the 6-month-old ones that the connection was made, and the 2 brief scraps of path snapped together into something much stronger. This is what astronomers mean by an observation arc. It is not a picture of the orbit. It is the span of time across which you have actually watched the thing move. 2 nights in June, by itself, gives you almost nothing. 2 nights in June joined to a night in December gives you the beginning of a real answer, because now you can see how the object curved. That is when the numbers started to move. Every night after the recovery, more observatories added positions. The orbit calculation was rerun each time, and each time it produced a family of possible paths rather than one path, because the measurements carry small errors and those errors spread as you project forward. The family of paths fanned out into a long thin cloud somewhere out in the future, and the question that automated software asks every single day, without drama, is whether the Earth sits inside that cloud. For 2004 MN4, the Earth sat inside the cloud. The date was the 13th of April 2029. At first, the probability was small, a fraction of a percent, the sort of number that appears on the risk pages of the Jet Propulsion Laboratory and the European Space Agency several times a year and disappears within a week. It usually disappears for a reassuring reason. More data narrows the cloud, and as the cloud narrows around the object's true path, the Earth falls outside it, and the probability drops to 0. That is the normal life cycle of an asteroid scare. The number goes up, then it goes to nothing, and almost nobody outside the field ever hears about it. but there is a cruel piece of arithmetic buried in that process. If the Earth happens to lie near the middle of the uncertainty cloud rather than at its edge, then narrowing the cloud does not push the Earth out. It concentrates the possibilities onto us. The probability rises, not because the asteroid has changed course, but because we are learning where it is actually going, and the answer keeps being here. Through the last week of December 2004, that is exactly what happened. Observations came in from Kitt Peak, from Australia, from observatories in Europe and Asia. The cloud tightened. The probability did not fall. It climbed, and it kept climbing day after day, while the people watching it grew steadily quieter. By the 27th of December 2004, the probability that this object would hit the Earth on the 13th of April 2029 had reached roughly 2.7%. Written as odds, that is about 1 in 37. Take a moment with that number, because it is easy to hear a small percentage and let it slide past. 1 in 37 is not a lottery ticket. It is roughly the chance of rolling 2 sixes with a pair of dice, twice as likely as being dealt a pair of aces in a hand of poker. Nobody would board a plane at those odds, and the consequence at the far end was not an inconvenience. A stone of that size striking the Earth would arrive with the energy of something like 1,000 megatons, enough to destroy a region the size of a small country, or to raise ocean waves along an entire coastline. It would not end the species. It would be, without competition, the worst day in recorded human history. There is a scale for this, invented by the astronomer Richard Binzel of the Massachusetts Institute of Technology and adopted by the international community in 1999. It is called the Torino scale, named for the Italian city where it was ratified, and it runs from 0 to 10. It combines 2 things: how likely an impact is and how much damage it would do, and it exists mainly so that scientists have a calm, agreed way to talk to the public about a subject that invites the opposite. Most objects that ever appear on it sit at 1, a level that means a routine discovery meriting attention but no alarm. Nearly all of them fall to 0 within days. The object designated 2004 MN4 reached level 4. 4 means a close encounter with a real chance of collision, capable of regional devastation, and it means that governments should be told. No object before it had gone above 1. No object since has gone above 3. It remains the highest rating ever assigned, and it was assigned during the week between Christmas and New Year, when most of the world's observatories were running on skeleton staff. What happened next has been quietly overwritten in the popular telling. There was no press conference, no emergency broadcast, no scramble of agencies. Stephen Chesley and Paul Chodas at the Jet Propulsion Laboratory and their counterparts working on the European risk lists did what the system is designed to have them do. They asked for more data, and they went looking for old data. That second move is the one that saved everybody a very bad decade. Sky surveys photograph enormous swathes of sky every clear night and archive everything, including the objects nobody noticed at the time. If an asteroid was in your frame in March and you did not know to look for it, the light is still sitting in your files. Astronomers call it a precovery, a recovery of an observation you already had. 2 researchers with the Spacewatch survey, Jeffrey Larson and Andes Score, went into the archive and searched images from the previous March in the exact region of sky where the newly computed orbit said the object should have been. They found it, and with that faint months-old smudge, the whole picture changed. Before we follow what those old images did to the numbers, the object needed a name, and the story of the name says something honest about the people who do this work. Asteroids get their formal number only when the orbit is nailed down well enough that the object can never be lost again. That happened here in the middle of 2005, and the object became Minor Planet 99,942. Once numbered, the privilege of naming belongs to whoever discovered it, subject to approval by a naming committee of the International Astronomical Union, which has veto power for anything commercial, offensive, or tediously self-serving. Discoverers have used that privilege on their spouses, their cats, jazz musicians, mountains, and at least one entire rock band. Tucker, Tholen and Bernardi chose Apophis. In Egyptian religion, Apep was a serpent of darkness and disorder, coiled somewhere beneath the horizon, who attacked the sun god Ra every night as Ra's boat passed through the underworld. Every night Ra survived, and morning came, and the next night the serpent returned. Apophis is the Greek rendering of that name. As a label for a rock that had briefly threatened to end a civilization, and had then slipped back into the dark, it is close to perfect. There was also a second reason, which the discoverers have never bothered to hide. Two of them were fans of a science fiction television series called Stargate, in which the principal villain is a parasitic alien who has taken the name and the imagery of the same Egyptian god. Tholen and Tucker liked the resonance, so a rock named for an ancient serpent of chaos carries, quietly, a nod to a 1990s television show, and both of those things are now permanently attached to a real object in a real orbit around a real star. The naming mattered more than it should have. A name is a handle, and a handle is what lets a story travel. Nobody outside the field was ever going to remember 2004 MN4. Everybody remembers the god of chaos. When the impact risk was later removed, the name stayed, and it kept generating fear long after the fear had lost its basis. Search for Apophis today, and you will find a great deal of material that treats the 2029 flyby as a coin flip, or as a thing agencies are hiding, and almost all of it leans on a name that 3 astronomers picked partly as a joke. Naming also had a practical function. When Apophis was numbered and named, it became a fixed point in the catalogue, an object that could be tracked continuously, targeted by radar, observed for decades. It stopped being a scare and became a subject. That transition is the most important thing that ever happens to a hazardous asteroid, and it happens exactly once, and it happens quietly. But none of this explains how the astronomers went from one chance in 37 to a confident all clear. To understand that, you have to understand what an orbit really is, and why knowing one is less like predicting the future, and more like measuring a room in the dark. An orbit is a shape, and a position on that shape, and nothing more. 6 numbers describe it completely. How large the ellipse is, how stretched it is, how it is tilted with respect to the plane of the planets, which way it points, and where the object sits along it at a given moment. Give a computer those 6 numbers and the mass of the Sun, and it will tell you where the object was in the year 1800 and where it will be in the year 3000. The catch is that we never measure those 6 numbers. We cannot. What we measure is a direction. A telescope tells you that on a particular second of a particular night, the object appeared at a particular spot on the sky, and that is all it tells you. It gives you an angle, not a distance. Every one of those angles is a line running outward from the Earth into space, and the asteroid is somewhere on that line, and you do not know where. So you gather many lines from many nights, and you look for the single orbit that would place the asteroid on all of them at the right moments. That is the whole trick, and it goes back to Carl Friedrich Gauss, who invented the mathematics in 1801 to recover the newly lost dwarf planet series, and found it again within a year of predicting where it would be. The lines are never perfect. A measurement of position on the sky carries an error of a fraction of an arc-second, which sounds trivially small, and at the distance of an asteroid corresponds to hundreds of kilometers, so there is never one orbit that fits. There is a whole family of orbits that fit almost equally well, differing from each other by amounts too small to detect today. Run that family forward 25 years and the small differences grow. 2 orbits that place the asteroid within a few kilometers of each other now will place it thousands of kilometers apart in 2029, because a tiny difference in speed accumulates into a large difference in arrival time, and the Earth is a moving target. The family of orbits spreads into a long, thin, curved tube of possibility, thousands of kilometers long and much thinner than it is long, and the asteroid is somewhere inside it. Impact probability is nothing more mysterious than the fraction of that tube that the Earth happens to be sitting in. When people say the odds were 1 in 37, what they mean is that about 1/37th of the plausible orbits ran through our planet. There are two ways to shrink a tube. You can watch the object for longer, which is slow, or you can add a measurement of a completely different kind, one that gives you what optical telescopes never give you. You can measure the distance directly. You can bounce a radio wave off the rock and time the echo. In Puerto Rico, in a natural sinkhole in the karst hills near the town of Arecibo, there used to be a dish 1,000 feet across. The Arecibo Observatory could not be steered. It stared at whatever the rotation of the Earth carried across its narrow window of sky, and it was, for more than half a century, the most sensitive radar instrument on the planet. On the 27th of January 2005, Arecibo transmitted a beam of radio energy at Apophis. Some minutes later, a whisper of that energy came back, and the observatory measured how long it had taken. Understand what that gives you. An optical telescope measures direction with an error that translates to hundreds of kilometers. Radar measures distance by timing an echo, and time can be measured with almost absurd precision. The Arecibo ranging measurements pinned the distance to Apophis to within about a kilometer, and a second quantity came free with it. Because the asteroid is moving toward or away from you, the returning radio wave is shifted in frequency, exactly as a train whistle drops in pitch as the train passes. That shift measures the speed along the line of sight, and it measures it to within a few millimeters per second. Radar does not tell you where the object is on the sky. It is nearly blind to that. What it tells you is where the object is along your line of sight and how fast it is coming or going, and those are precisely the quantities that optical astronomy is worst at. The two techniques fail in opposite directions, which is why combining them is so violently effective. A single radar detection can shrink the uncertainty tube by a factor that a year of ordinary tracking could not touch. Arecibo observed Apophis again in August of 2005 and again in May of 2006, and the tube tightened each time. The observatory kept doing this for hundreds of near-Earth asteroids, quietly, year after year, until the platform above the dish collapsed into the sinkhole in December of 2020 and the instrument was lost. The Goldstone antennas in the Mojave Desert still do this work, and so does the Greenbank telescope in West Virginia, which can receive a radar echo transmitted by Goldstone. But the loss of Arecibo removed most of the world's radar sensitivity in a single afternoon, and it has not been replaced. There is a limit worth stating, honestly. Radar only reaches out a certain distance, because the returning signal weakens as the fourth power of range, which means an object twice as far away sends back 1/16 of the echo. Apophis can only be ranged when it comes reasonably close. Most of the time it is beyond reach, and we are back to angles. So by the middle of 2005, astronomers had a very tight tube of possibilities for a rock that had, a few months earlier, carried the highest impact rating ever assigned. What they did with it depended on those old photographic frames from March, sitting in the Spacewatch archive that Larson and Descore had gone back to find. Old data is worth more than new data, and the reason is simple once you see it. The strength of an orbit determination depends less on how many observations you have than on how long a stretch of the orbit they cover. Adding 100 measurements from this week barely helps, because the object has hardly moved along its path. Adding a single measurement from 9 months ago extends the arc backward, and it does so at a point where the asteroid was somewhere completely different in its journey around the Sun. The Spacewatch images from the 28th of March, 2004, showed Apophis nearly 3 months before anyone knew it existed. Faint, unlabeled, ignored at the time, sitting in a file on a hard disk in Arizona. Those positions extended the observation arc, and when they were folded into the orbit calculation, the possibility tube for 2029 shifted and narrowed, and the Earth fell outside it. That was the 27th of December 2004. The 2.7% went to zero in a single afternoon, and it went to zero because of light that had entered a telescope 9 months before from an object nobody had noticed. The Trina rating dropped from 4 to 0, and then, as the radar data arrived through 2005 and 2006, the position of Apophis on the 13th of April 2029 resolved into something remarkably specific. It would pass close, astonishingly close. It would not pass through us. You might think that ends the matter. It did not, and the reason is one of the more elegant and unsettling facts in the whole of celestial mechanics. When Apophis swings past the Earth in 2029, our gravity will grab it and fling it onto a different orbit. This is not a subtlety. It is a violent alteration. The asteroid's year around the Sun, currently a little under 324 days, will be stretched to something well over a year. Its path will be lifted and twisted. Apophis will leave that encounter as a fundamentally different object from the one that arrived. And the details of that new orbit depend exquisitely on exactly where Apophis passes. Shift the flyby distance by a few hundred kilometers, and the outbound path shifts by millions of kilometers decades later. The Earth's gravity acts as an amplifier, taking the small uncertainty in the approach and blowing it up into a large uncertainty in everything that follows. So the question was never really about 2029. Once we knew Apophis would miss, the worry moved downstream to the years 2036 and 2068, when the asteroid's altered orbit would bring it back to our neighbourhood. Whether those return visits were dangerous depended on where, within a corridor tens of thousands of kilometres wide, the asteroid threaded the eye of the 2029 encounter. Somewhere in that corridor, astronomers realised there was a small window. Pass through it, and you come back and hit us. Miss it, and you never do. They call it a keyhole, and the name comes from Paul Chodas at the Jet Propulsion Laboratory, who used it to describe a thing that had been known mathematically for years, but had never had a word that ordinary people could hold on to. Picture the flyby as the asteroid crossing a vast invisible screen stretched across space near the Earth. Every point on that screen corresponds to a slightly different trajectory in, and therefore to a slightly different orbit out. Most points send the asteroid off on some new path that never brings it back into contact with us. But a few points, scattered across the screen, send it out on an orbit whose period is exactly right, some clean ratio of the Earth's year, so that after a certain number of laps around the Sun, the asteroid and the Earth arrive at the same crossing point at the same instant. Those special points are the keyholes. They are small. The keyhole on the 2029 screen that would have delivered Apophis into the Earth in 2036 measured about 600 metres across. 600 metres on a screen tens of thousands of kilometres wide. Threading it would have been like a rifle shot from the far side of a continent hitting the centre of a dinner plate, except that nobody is aiming and the shot has been in flight for millions of years. There are hundreds of keyholes on that screen, corresponding to different return years, most of them far smaller than the 2036 one. A keyhole for the year 2068 sat elsewhere on the screen, and it stayed on the list of possibilities for a decade and a half. The keyhole idea has a practical edge that is easy to miss. If you ever discover that an asteroid is heading for a keyhole, you do not need to move it far. You need to move it a few hundred meters, years in advance, which is well within reach of the technology we already have. Deflecting an asteroid away from the Earth itself might require shifting it thousands of kilometers. Deflecting it away from a keyhole requires shifting it by the width of a small farm. The keyhole is the leverage point, and it is why planetary defense people talk about warning time the way surgeons talk about early detection. But there is a shadow side. To know whether an asteroid is heading for a keyhole, you must know its position years ahead to within a few hundred meters. That is an extraordinary standard of prediction for a body 200 million kilometers away. Radar helps enormously, and long observation arcs help, and still it is not always enough. Because there is a force acting on Apophis that is not gravity. It is so gentle that it would take a laboratory instrument to notice it in an afternoon. Over decades it moves the asteroid by hundreds of kilometers, and it acts unequally on every rock depending on its colour, its shape, its spin, and how well it holds heat. It is sunlight, and it does not push the way you would expect. An asteroid in daylight absorbs sunlight on the side facing the sun. That much is obvious, and the resulting pressure of the light itself is real, but almost negligible for anything larger than a pebble. The interesting part happens later. The rock warms where the light lands, and then it rotates, carrying the warm surface around toward the night side, where it slowly radiates that heat away as infrared. Radiation carries momentum, so the asteroid is being pushed very gently by its own escaping warmth. And because the warmest part of the surface is not the part facing the sun, but the part that has just turned away from it, the push does not point straight outward. It points sideways, along the direction of travel or against it. This is the Yarkovsky effect, named for Ivan Osipovich Yarkovsky, a Polish-Russian civil engineer who described it in a pamphlet around the turn of the 20th century and was almost entirely ignored. The Estonian astronomer Ernst Öpik happened to read the pamphlet, remembered it decades later, and mentioned it in print in the 1950s. That accident of memory is the only reason the idea survived. The force is absurdly small. On Apophis, it amounts to something like the weight of a few grains of sand. But it never stops, and it acts in the same direction for years at a time, and an asteroid has no friction to fight it. Over a century, that whisper of a push will move a rock like Apophis by tens of thousands of kilometers along its orbit. It is the difference between hitting a keyhole and sailing past it. Which way it pushes depends on which way the asteroid spins. A rock rotating one way is nudged outward, drifting slowly away from the sun. A rock rotating the other way is nudged inward. The size of the effect depends on how dark the surface is, how rough, how good the rock is at storing heat overnight. Every one of these is a property we must measure individually for every hazardous asteroid, because you cannot look up the answer in a table. David Tholen, one of the original discoverers, spent years chasing the Yarkovsky drift of Apophis. By 2013, he and his colleagues had detected it. The asteroid was drifting inward, toward the sun, by a couple of 100 meters per year relative to where pure gravity said it should be. Small, utterly decisive for a 600-meter keyhole 3 decades away. Detecting that drift is what finally let the 2068 possibility be addressed, rather than merely worried about. It also carries a lesson that reaches past this one asteroid. A prediction of an impact 50 years out is not really an exercise in gravity. Gravity is the easy part, solved in the 1680s. The hard part is the thermal physics of a specific rock whose colour and spin and internal structure we have never measured. To settle Apophis, astronomers needed one more radar campaign, and in March of 2021 they got the last good chance for 8 years. In early March 2021, Apophis passed within about 17 million kilometres of the Earth, a distance that sounds enormous and is, by the standards of planetary radar, just barely within reach. Arecibo was gone by then, collapsed 3 months earlier, so the observation was made the hard way. The 70-metre antenna at Goldstone in the Mojave Desert transmitted, and the echo, returning after nearly 2 minutes of round trip, was collected both at Goldstone itself and at the 100-metre Greenbank Telescope in West Virginia, more than 3,000 kilometres away. Splitting transmission and reception between 2 dishes on opposite sides of a continent gains you sensitivity you could not get from either alone. The measurements were led at the Jet Propulsion Laboratory by Marina Brozovic and, on the orbit side, by David Finocchia at the Centre for Near-Earth Object Studies. The radar pinned the asteroid's distance to within a few hundred metres and its line-of-sight speed to a fraction of a millimetre per second. Folded together with 17 years of optical positions and the measured Yarkovsky drift, the result was a trajectory of extraordinary confidence. Apophis will not strike the Earth in 2029. It will not strike in 2036. It will not strike in 2068. It will not strike at any point in the next 100 years, and the 2068 keyhole, the last one that had held any credible possibility, was formally excluded. On the 26th of March, 2021, Apophis was removed from the risk list maintained by the Jet Propulsion Laboratory. and from the corresponding list kept by the European Space Agency. The most famous dangerous asteroid in the world stopped being a dangerous asteroid, and the announcement was made in a short press release that almost nobody read. Farnokia said something at the time that is worth carrying with you. With the radar data, the position of Apophis in 2029 is known so well that the uncertainty shrank from hundreds of kilometers to a handful. Beyond 100 years, honesty requires a different tone. The 2029 flyby will scramble the orbit so thoroughly that predictions past the middle of the next century become genuinely uncertain, not because our methods fail, but because the encounter amplifies every small unknown. Astronomers do not claim otherwise. They also point out that we will have another century of observations and better instruments than these, and that the asteroid will be one of the most heavily monitored objects in the solar system throughout. So the fear evaporated, and what was left behind was something more interesting than fear. A 300-metre body from the population that has shaped the surface of every world in the inner solar system was going to come closer to the Earth than any object of its size in recorded history, on a date we knew, at a place we could compute. The question stopped being whether Apophis would hit us, and became something a scientist finds much more urgent. What exactly is it? Light carries a chemical signature. When sunlight reflects off a mineral surface, certain wavelengths are absorbed more strongly than others, according to which atoms sit in the crystal lattice, and the light that comes back to us is subtly reddened or dimmed in patterns that a spectrograph can read. Spread that reflected light into a spectrum and you are, in a real sense, looking at the rock. Apophis was measured this way, notably by Richard Binzel and colleagues, and the answer came back clearly. It belongs to the group astronomers call S-type, which is shorthand for stony. Its surface is silicate rock, the family of minerals built around silicon and oxygen that makes up most of the crust of the Earth, mixed with grains of metallic iron and nickel. More precisely, its spectrum matches a class of meteorite called an LL chondrite, one of the most common kinds of stone that falls out of the sky and lands in a field. That is not an abstract identification. We have LL chondrite meteorites in drawers, in museums, in laboratories. You can hold one. It is dense, grey inside, flecked with metal, and it is made of small round beads called chondrules that condensed from the solar nebula 4.5 billion years ago and never got melted into anything larger. Apophis is a heap of that material, unchanged since before the Earth finished forming. There is a comparison closer at hand. The Japanese spacecraft Hayabusa visited an S-type near-Earth asteroid called Itokawa in 2005 and brought grains of it back to Earth in 2010, the first samples ever returned from an asteroid. Itokawa turned out to be an LL chondrite as well, and its structure was a revelation. It was not a solid boulder. It was a pile of rubble, gravel and stones and dust held together by their own feeble gravity, with roughly 40% of its volume being empty space between the pieces. Whether Apophis is also a rubble pile is one of the central open questions, and the honest answer today is that we suspect so and do not know. Most asteroids in this size range appear to be. Objects a few hundred meters across have been broken and reassembled repeatedly across the age of the solar system, and the sharp, monolithic boulder is the rarity rather than the rule. The distinction is not academic. A solid rock and a loose pile respond to a shove in completely different ways. Strike a monolith with a spacecraft and you transfer momentum cleanly. Strike a rubble pile and it may absorb the blow, or it may throw off far more debris than the impactor's own mass, which multiplies the push. Approach one closely and its gravity field is lumpy and strange. Pass it near a planet and a loose pile may deform, or shed material, or come apart entirely. That last point is not idle. In 2029, Apophis will pass close enough that the Earth's gravity will pull harder on its near side than its far side, and something is going to give. To understand what, you need to know what shape it is and how it turns. Apophis has never been photographed, not properly. Every image you have seen of it is either a radar map or an artist's painting. Radar imaging is a strange craft. You do not get a picture in the ordinary sense. You get a distribution of echo strength across two axes, one being distance from the antenna and the other being the frequency shift caused by rotation, and you reconstruct a shape from that. The radar observations from 2012 and 2013, and again in 2021, produced maps in which each pixel corresponds to about 38 meters of the asteroid's surface. Everything smaller than a football stadium is invisible. What the maps show is an elongated body with two lobes, narrower in the middle, of the kind that has been found again and again among near-Earth asteroids. Itokawa has it. The comet nucleus that the Rosetta spacecraft studied has it, dramatically, somewhere between a peanut and a poorly made snowman. The mean diameter is around 340 meters, and the long axis is at least 450, and those numbers still carry uncertainties of tens of meters, which for a body we have tracked for 2 decades is a humbling thing to admit. The rotation is stranger. Most asteroids spin about a single fixed axis, like a top. Apophis does not. It tumbles. Careful measurements of its changing brightness, led by Peter Pravec and colleagues at the Ondřejov Observatory in the Czech Republic, showed 2 different periods overlapping. The asteroid rotates about its short axis in roughly 27 hours, while the axis itself swings around in a slow procession taking about a day and a quarter. The combination means Apophis has no stable up. A person standing on its surface would watch the sun rise and set on a schedule that never quite repeats. Tumbling is a clue, and what it points to is a collision. Left alone, an asteroid's internal friction gradually damps a tumble into simple rotation, over timescales of tens or hundreds of millions of years for a body this size. Apophis is still tumbling, which suggests it was struck, or gravitationally disturbed by a close planetary pass, more recently than that. It has had a violent adolescence. The tumble also has a practical bite. If you are designing a spacecraft to orbit a body, you would like its gravity field to hold still. If you want to land on it, you would like to know which way is down. Apophis offers neither. Any mission that goes there must navigate a lumpy, wobbling, slowly cartwheeling mountain whose exact mass is unknown to within a factor that matters. And the tumble is about to change. Tidal forces during the 2029 encounter are expected to alter both the spin rate and the wobble in a way that models can predict only roughly, because the prediction depends on the internal structure we cannot see. This is what makes Apophis so valuable. Not what it is, but what it is about to become. Before we get there, though, one more question remains about the rock itself, how it came to be crossing our path at all. Apophis was not born where we find it. Nothing in near-Earth space was. An asteroid on an Earth-crossing orbit has a short life. It will either strike a planet or be flung out of the solar system by a close encounter, or fall into the sun, and it will do one of those things within a few tens of millions of years. That is a long time by human reckoning, and a blink against the 4.5 billion years the solar system has been running. If near-Earth asteroids had been placed here at the beginning, they would all be gone. So they are being resupplied. The source is the main asteroid belt, the broad zone between Mars and Jupiter, where several 100,000 catalogued bodies orbit, most of them small, all of them fragments of a planet that never assembled, because Jupiter's gravity kept stirring the material too violently for it to stick. Getting a rock out of the belt and into our neighbourhood requires a specific mechanism, and it turns out to be a 2-stage machine of remarkable delicacy. The first stage is the Yarkovsky effect, the same feeble thermal push we met earlier. It causes small asteroids in the belt to drift slowly inward or outward, by perhaps 100 meters a year, wandering across the belt over tens of millions of years. The second stage is a resonance. At certain distances from the Sun, an asteroid's orbital period falls into a simple ratio with Jupiter's, or its orbit precesses at the same rate as Saturn's, and the repeated gravitational tugs stop cancelling out and start adding up. The most powerful of these lies at the inner edge of the belt and is called the NU6 resonance, where the slow wobble of an asteroid's orbit keeps step with the slow wobble of Saturn's. An asteroid that drifts into it does not merely shift. Its orbit is stretched, over a few 100,000 years until the inner end of that orbit dips down into the region of the terrestrial planets. So the picture is this. Apophis spent most of the age of the solar system as an anonymous fragment somewhere in the inner asteroid belt, perhaps part of a larger parent body that was shattered in a collision, drifting a few 100 meters a year on the pressure of its own escaping heat. At some point, probably within the last several million years, it drifted into a resonance and was pulled inward, and the resonance handed it to the inner solar system, and now it crosses our orbit twice a year. Its ancestry may be traceable. Some researchers have linked LL chondrite material and the near-Earth objects that match it back to a specific collisional family in the inner belt, a swarm of fragments from a breakup hundreds of millions of years ago. If that link holds, Apophis has cousins, and we have some of them in meteorite collections already. Its future is a matter of arithmetic that starts on a Friday evening in April. Right now, Apophis takes about 324 days to circle the Sun. Its year is shorter than ours. That places it in a group called the Atens, named for the asteroid Aten, and defined by a simple property. Their orbits are on average smaller than the Earth's, even though they swing out far enough to cross our path. An Aten spends most of its time inside our orbit, sunward of us, in the part of the sky that from our vantage point lies close to the glare of daylight. It laps us. It gains on the Earth roughly every 8 years, and the two orbits touch in April, which is why the close approaches cluster in that month. Because Apophis's year and Earth's year are near a ratio of 6 to 7, the encounters repeat with a rhythm. 7 Earth years is almost exactly 8 Apophis years, so roughly every 7 springs the two of us are back in the same relative arrangement, sometimes near, sometimes far. 1968, 2004, 2021, and now 2029 sit on that rhythm. Here is a detail that most retellings of Apophis leave out entirely, and it is one of the best. The flyby will not merely bend the asteroid's path, it will move it into a different family. As Apophis passes the Earth, our gravity will add energy to it, enlarging its orbit and stretching its year from just under 324 days to something over 400. Its average distance from the Sun will rise above the Earth's. From that instant, it will no longer be an Aten. It will be an Apollo, a member of the group whose orbits are larger than ours and cross ours from outside. Astronomers have watched asteroids change orbits before. They have never had advance notice to the day that a well-studied object was about to change its formal classification, with 2 spacecraft in position to watch it happen. The taxonomy of the solar system will be rewritten for one object in about an hour by nothing more exotic than the Earth passing by. Everything about the encounter is decided by geometry we already know. Apophis will approach from the sunward side, which means it will be lost in daylight in the days before, invisible to every ground telescope on the planet. It will come up around the Earth and pass beneath us, below the South Pole, at closest approach. Then it will recede on the night side, into the evening sky. The last approach of this magnitude by an object this large, in recorded history, did not happen. Statistically, an encounter this close by a body this size occurs about once every 7,000 or 8,000 years. It is not merely rare in our lifetimes. It is rare on the scale of agriculture, and unlike almost every rare event in astronomy, this one will be seen by ordinary people, standing in ordinary places without instruments. At its closest, sometime after 21 hours, universal time on the 13th of April 2029, Apophis will be about 31,600 kilometers above the surface of the Earth. Some numbers to hang that on. The Moon sits at an average of 384,000 kilometers, so Apophis will come about 12 times closer than the Moon. The satellites that carry television and much of the world's long-haul communications sit in geostationary orbit, 35,786 kilometers above the equator, and Apophis will pass beneath them. The distance is roughly 2.5 Earth diameters. It is less than the distance you would cover driving around the equator, and considerably less than 1/5 of the way to the Moon. None of this brings it near enough to touch the atmosphere, which thins into nothing a few hundred kilometers up. It is not a near miss in the sense of a bullet passing your ear. It is a near miss in the sense that a body of that size has almost certainly not come this close since before the invention of writing. From the ground, the asteroid will brighten as it approaches. At its best, it should reach about third magnitude, which is the brightness of a typical star in a familiar constellation, easily visible from a dark countryside and visible from the edges of a town, though a city centre will probably wash it out. It will look like a star that will not stay put. It will cross the sky at up to about 42 degrees per hour at its fastest, which is more than a full width of your outstretched hand every 10 minutes. Follow it with binoculars, and it will drift steadily out of the field of view while you watch. The visibility path runs across the Eastern Hemisphere. Observers across most of Europe, across Africa, and in Western and Central Asia will have the asteroid in their evening sky, weather permitting. Estimates put the number of people who could step outside and see it, if they knew when to look, at around 2 billion. The Americas will miss the closest approach, the Earth having turned the wrong way at the wrong moment. 2 billion people. That is a number without precedent in the history of astronomy. No comet, no eclipse, no aurora has ever delivered an event that's specific to that many pairs of eyes at once. And the object they will be watching is the same class of body that killed the dinosaurs, only much smaller, moving on a path that we understand well enough to have ruled out disaster 25 years ahead of time. There will be another effect, harder to notice and easy to overlook. The Earth's gravity will not only bend Apophis's path, it will pull unevenly on the asteroid itself, tugging the near side harder than the far side. For a solid rock, that difference is nothing. For a loose pile of gravel held together by almost no gravity of its own, it is a slow, silent earthquake. Tidal force is a difference, not a pull. The Earth attracts the near face of Apophis slightly more strongly than its centre, and the centre slightly more strongly than the far face, and the result is a gentle stretch along the line to the Earth and a squeeze across it. For Apophis, at 31,000 kilometres, the stretch is far too weak to tear the asteroid apart. It is not weak enough to be ignored. On a body whose surface gravity is roughly 100,000 times feebler than Earth's, where a person could jump off and never come back, and a loose pebble sits in place only because nothing has disturbed it, a small change in the local gravity field is a large change in what stays put. Models built by researchers including Derek Richardson and Yun Zhang suggest several things may happen. The spin state should change, because the tidal torque acts on an elongated body like a hand on a wrench, and the tumble that Pravec measured could be sped up, slowed down, or reoriented. Loose material on the surface may be set in motion, sliding downslope where slopes exist, in avalanches that would take minutes to unfold and would move at the speed of a person walking. Boulders that have sat undisturbed for 1 million years may shift. Some fine dust may be lifted clear of the asteroid entirely. Beneath the surface, the regolith could be shaken hard enough to compact or to loosen. Seismic waves would ring through the interior, and how they travel depends entirely on whether Apophis is one rock, a few large pieces in contact, or a heap of rubble. The shaking would refresh the surface, exposing material that has been buried and shielded from the solar wind and cosmic rays, material that has not seen sunlight in aeons. Patrick Michel, who directs research at the French National Centre for Scientific Research and works at the Côte d'Azur Observatory, has made the point that has become the guiding argument for everything that follows. To study how asteroids respond to forces, we have had to travel to them and perform experiments ourselves at enormous cost with a single spacecraft on a single body. Here, for the first time, nature brings the asteroid to us and performs the experiment on its own. All we have to do is arrive in time to watch. That is the whole scientific case in 2 sentences, and it is what turned a defunct impact scare into the most anticipated planetary encounter of the decade. Not the danger, the opportunity, a full-scale experiment on the internal structure of a rubble pile conducted by the Earth, free of charge, on a date we have known since 2004. But an experiment is worthless without instruments, and the instruments have to be there before the experiment begins. Ground telescopes cannot help in the crucial window. Apophis approaches out of the sunlit sky and departs back toward the sun's glare, and for weeks around the event it is nearly unobservable from here. To see the before and the after, something has to fly out and meet it. Europe's answer is a spacecraft named Ramses, which stands for Rapid Apophis Mission for Space Safety, and the word rapid is not decoration. It is the entire engineering problem. A normal planetary mission takes 10 to 15 years from first proposal to launch. Ramses has to be at Apophis by February of 2029, 2 months ahead of the flyby, which means it must leave Earth in April of 2028. The date cannot slip. The asteroid will not wait for a delayed rocket the way a Mars window forgives you, and reopens in 26 months. So the European Space Agency did something unusual. It began building before it was allowed to. In 2024, with no approved budget, the agency's Space Safety Program Board granted permission to start preparatory work using existing resources, betting that the money would follow. The formal commitment came at the Ministerial Council meeting in November of 2025, when Europe's space ministers voted to fund the mission properly. In May of 2026 in Berlin, the heads of the European and Japanese space agencies signed the cooperation agreement that made Ramses a joint venture. Japan's contribution is substantial. The Japan Aerospace Exploration Agency will supply the solar arrays and a thermal infrared imager, an instrument that measures how the asteroid's surface holds and releases heat. That measurement bears directly on the Yarkovsky drift we met earlier, and on the question of how much loose dust lies on the surface, since fine powder cools quickly at night and solid rock does not. Japan will also launch the mission on an H-3 rocket from Tanegashima. The way Ramses gets built in 4 years is by not being new. It reuses the design, the teams, and much of the hardware of Hera, a European spacecraft already flying, which we will come to shortly. Copying a proven spacecraft is unglamorous, and it is the only reason this mission exists at all. Ramses will not orbit Apophis in any comfortable sense. The asteroid's gravity is so weak that the spacecraft will fly in slow, carefully managed loops around it, more hovering than orbiting, with the sun's light pressure competing against Apophis's own feeble pull. It will spend February and March of 2029 mapping the surface, measuring the shape, timing the tumble, tracking the orbit, and weighing the asteroid by watching how its gravity nudges the spacecraft. It will carry 2 small companions, each about the size of a shoebox stack. One will fly around Apophis on its own path, the other is intended to touch down on the surface, and by studying how it bounces and settles, tell us how firm the ground is. Then Ramses will hold station and watch while the Earth swings past. That is the entire point. Before and after, measured by the same instruments, on the same body, across the same few hours. Every parameter that changes is a direct measurement of the asteroid's interior. If the spin shifts, the mass distribution is revealed. If landslides happen, the surface friction is revealed. If nothing at all happens, that is a result too, and it would tell us that rubble piles are stronger than we think, which would be an unwelcome and extremely valuable thing to learn. Europe will be there first, the United States will arrive late, and by design, aboard a spacecraft that has already done one of the hardest things anybody has ever done in the solar system. On the 24th of September, 2023, a capsule the size of a car tyre came through the atmosphere over Utah and landed in the desert under a parachute. Inside it were 120 grams of the asteroid Bennu, scooped from the surface by a spacecraft called OSIRIS-REx after 7 years of flight. The spacecraft itself never landed. It released the capsule on the way past, fired its thrusters 20 minutes later, and kept going. It had fuel left, and NASA had a decision to make. The decision was Apophis. The spacecraft was renamed OSIRIS-APEX, the last 4 letters standing for Apophis Explorer, and the leadership passed from Dante Lauretta, who had built the Bennu mission over 2 decades, to Danny Mendoza della Giustina at the University of Arizona. Half the science team stayed behind to study the grains from Bennu. The other half turned to a rock they would not reach for 6 years. The route is not direct. To catch Apophis, the spacecraft must loop around the Sun several times, and one of those loops carries it closer to the Sun than it was ever designed to go. On the 2nd of January 2024, OSIRIS-APEX passed some 40 million kilometers nearer the Sun than its engineers had ever intended, and the thermal analysis said certain instruments might not survive. They did. 2 of them came through in better condition than before, apparently because the heat baked contaminants off their optics. Orbital mechanics dictates the timing, and orbital mechanics is unsentimental. OSIRIS-APEX cannot be at Apophis before the flyby. It will pass the Earth about an hour behind the asteroid, using our gravity for a final push, and then spend weeks closing the gap. It arrives in late June of 2029, some 10 weeks after the encounter, and it will stay for 18 months. That lateness turns out to be a strength. Ramses will have the before and the immediate after. OSIRIS-APEX will have the long after, the slow settling of disturbed material, the new spin state measured over many rotations, the surface as it looks once the dust has come down, and then it will do something that no spacecraft has done to an asteroid. It will descend to within a few meters of the surface and fire its thrusters at the ground, blowing away the top layer of dust and gravel to expose whatever lies underneath. This is not sampling, it is excavation by rocket exhaust, and it works only because the gravity is so weak that a puff of gas can move tons of material. What it exposes will be rock that has never been touched by sunlight or the solar wind, the unweathered interior of a body that formed with the planets. There is a shadow over this. NASA's budget proposal for the 2027 fiscal year contained no money for OSIRIS-APEX. Congress had already overridden a similar proposed cancellation the year before. The spacecraft is flying, healthy, fueled, and pointed at the most anticipated planetary encounter in a generation, and whether it is funded to arrive is a question that will be settled in committee rooms rather than in orbit. Chinese researchers have proposed their own Apophis mission, with 2 spacecraft. Whether it flies is undecided. Meanwhile, everything else depends on telescopes, and telescopes have a problem. The problem is the Sun. Apophis will approach the Earth from the sunward side, which means that for weeks before the encounter, it sits in the daytime sky, drowned in the glare of scattered sunlight. Ground telescopes will not see it coming. In the final hours, as it swings around and beneath us, it emerges into the evening sky and brightens rapidly, and for that single evening it belongs to everyone. Then it recedes, and here is the piece almost nobody mentions. As Apophis departs, its new orbit carries it back toward the region of sky near the Sun, and it becomes unobservable again almost immediately. For roughly the first several weeks after the flyby, the moment when the asteroid's spin and shape and orbit have just been rewritten, Earth's telescopes cannot look at it. The most scientifically valuable period in the history of this object falls into a blind window. That is precisely the gap the spacecraft are built to fill. Ramses is there through it. OSIRIS-APEX arrives at the end of it. Without them, we would watch the experiment begin, lose sight of the apparatus, and pick it up again months later, with the result already cooled. What the ground can do, it will do heavily. Radar is the sharpest tool. The Goldstone antenna in the Mojave will range Apophis before and after, measuring distance to hundreds of meters and speed to fractions of a millimeter per second, and the Greenbank telescope in West Virginia will listen for the echoes. Those measurements will pin the outgoing orbit with a precision that will settle the asteroid's future for centuries, and they will do it within days. Optical telescopes will measure the light curve, the rise and fall of brightness as an irregular body turns. That is how Peter Pravec found the tumble, and it is how the new tumble will be found. It requires nothing exotic. A modest telescope, a sensitive camera, and many nights of patient photometry, much of it done by amateurs who contribute a real and substantial share of the world's asteroid data. Spectrographs will look for changes in the surface. If the tidal shaking exposes fresh material, the colour of Apophis will shift, because rock that has been sitting in the solar wind for millions of years is darker and redder than rock that has just been uncovered. Astronomers call the process space weathering. Watching it undone, in real time on a known body, would answer a question that has hung over asteroid spectroscopy for decades. Whether the S-type asteroids and the stony meteorites in our drawers are the same material wearing different faces, and 2 billion pairs of eyes will do the thing that no instrument does, which is to look up and understand that this is a real object, in a real orbit, and that it has been there the whole time. None of this is fear. All of it is preparation. Because the reason we care so much about the interior of one harmless asteroid is that the next one may not be harmless, and moving a rock requires knowing what the rock is made of. Suppose you find an asteroid, and the calculation says it will hit the Earth in 15 years. What you do next depends almost entirely on a number you do not have. The number is how the asteroid responds to being pushed. Everything else is arithmetic you can do on a laptop. Where the asteroid is, where it will be, how much you need to move it, when you need to move it. Those are known or knowable. What is not knowable from a distance is what happens when you actually apply the force. Strike a solid block of stone with a spacecraft and the physics is textbook. The spacecraft's momentum is transferred to the block speeds up slightly, and you can compute the result before you launch. Strike a rubble pile and something more interesting happens. The impactor buries itself, and the collision blows a plume of gravel and dust off the surface at high speed. That plume carries momentum away in the opposite direction to the ejected material, which is to say it pushes the asteroid further, like a rocket firing out of the crater. The total shove can be several times larger than the impactor delivered by itself. Astronomers write this multiplier as the Greek letter beta, and it is the single most important unknown in kinetic deflection. Beta depends on porosity, on how tightly the material is packed, on grain size, on cohesion, on the strength of whatever weak forces hold dust to gravel in near zero gravity. Beta might be 1.5, it might be 4. If you're counting on a shove and you get a third of what you planned, you have wasted 15 years and the asteroid arrives on schedule. And there is a worse case. Push a rubble pile too hard or in the wrong place, and it may come apart. You would then have a cloud of fragments on a collision course rather than a single object, and depending on the sizes that could be better or considerably worse. A body that would have made one crater becomes a spray of city killers arriving over an hour. You cannot learn beta by staring at a telescope. Reflected light tells you the colour of the surface and nothing about how the rock is glued together. Radar penetrates a few meters at best. Even the mass, which sounds like something you could weigh from afar, requires a spacecraft close enough to be pulled by it. This is why Apophis matters far beyond Apophis. Tidal shaking is a force applied to the whole body, and the way the body responds is a direct readout of its internal strength. Landslides tell you the friction angle of the surface material. A change in spin tells you how the mass is distributed inside. Whether the asteroid deforms tells you whether it is one rock or 10,000. Nature is running the experiment. The instruments will be present, and the result generalizes, because Apophis is an ordinary member of the population that actually threatens us, a stony body a few hundred meters across, the size class that would ruin a region rather than a planet, and the size class that we have found less than half of. Before Apophis, though, we did an experiment of our own. We chose a rock nobody cared about, and we hit it as hard as we could. The target was chosen because it made the answer measurable. Didymos is a near-Earth asteroid about 780 meters across, and it has a moon. The moon is called Dimorphos, roughly 160 meters wide, orbiting its parent at a distance of about a kilometer, going around once every 11 hours and 55 minutes. That orbital period is the key. Measuring the speed of an asteroid around the Sun to the precision you would need to detect a small deflection is very hard. Measuring how long a moon takes to circle its parent is easy, because you watch from Earth as Dimorphos passes in front of and behind Didymos, and the brightness of the pair dips at each crossing, and you time the dips. Change the moon's orbit and the dips arrive at different times. The measurement can be done with modest telescopes, so NASA built a spacecraft the size of a vending machine, launched it in November of 2021, and drove it into Dimorphos at 6.1 kilometers per second on the 26th of September 2022. The mission was called the Double Asteroid Redirection Test. Its final images, streaming back at 1 per second, showed a grey landscape of boulders rushing up, and then the signal ended. Riding along, released 2 weeks earlier, was a small Italian spacecraft named Lycia Cube, which flew past 3 minutes after impact and photographed the aftermath. It saw a plume of ejected material spreading in filaments and streamers, thousands of tons of it, blown off the asteroid. The prediction, before impact, was that the orbital period of Dimorphos would shorten by something like 10 minutes, and that 73 seconds would count as a success. It shortened by 32 minutes. The extra came from the plume. Beta, the multiplier we could not measure any other way, turned out to be somewhere around 3.5, meaning the escaping debris pushed roughly 2.5 times harder than the spacecraft itself. The rock was loose, and its looseness made the deflection far more effective than the conservative planning had allowed. It did more than that. Later analysis of the light curve and modelling suggested Dimorphos was not merely dented, but reshaped, deformed from a slightly flattened sphere into something more elongated, and that boulders were sent tumbling across it. Roughly 30 large rocks were flung off entirely, and a swarm of them is now drifting in slow formation through the inner solar system, a scattering of debris that will remain traceable for years. The experiment worked. Humanity moved a natural body in space, deliberately, for the first time, and measured the result. What it did not do is tell us why it worked so well. Beta was measured for one object of one composition, with one internal structure, struck at one angle, at one speed, in one place on its surface. Whether the same shove applied to Apophis would give 3.5 or 1.5 remains unknown, and the crater that DART made could not be seen from Earth. The spacecraft that made it was destroyed making it. Somebody had to go back and look. Hera left Earth on a Falcon 9 on the 7th of October 2024, 2 years and 11 days after DART's last transmission. It is a European spacecraft, roughly the size of a small car, and its purpose is not to hit anything. It is to arrive at Didymos and Dimorphos and perform the forensic examination that turns a spectacular demonstration into usable physics. Ian Carnelli manages the mission for the European Space Agency, and Patrick Michel, whose argument about nature running the experiment we heard earlier, leads its science. The route ran past Mars in March of 2025, using the planet's gravity for a course change and taking the opportunity to photograph Deimos, the smaller and less visited of the 2 Martian moons, from a few thousand kilometers away. It arrives at Didymos in the closing weeks of 2026. The central measurement is mass. DART told us how much the orbit changed. It did not tell us how much mass had to be moved to change it, because nobody has ever weighed Dimorphos. Without the mass, the momentum transfer cannot be computed, and Beta remains a number with a wide error bar around it. Hera will weigh the moon by flying close and letting itself be pulled, tracking its own deflection with radio signals sent to Earth. Then the crater. Hera will map it in detail, measure its width and depth, and the pattern of ejected material around it, and from that shape, engineers can work backwards to the strength of the material and how the energy was partitioned between crushing rock and throwing it. Hera carries 2 small companions, each roughly the size of a shoebox. One is named Milani, after the Italian mathematician Andrea Milani, who developed much of the theory of impact monitoring that underlies the risk lists we discussed. It will study the surface minerals and the dust cloud. The other is named Juventus, and it carries a low-frequency radar designed to see through Dimorphos, to send radio waves in one side and read what comes out, and thereby produce the first look at the inside of an asteroid. If Dimorphos is a rubble pile, Juventus will show the rubble. If there is a solid core, it will show that instead. Juventus is also meant to land, at the end of its mission, in the gentlest touchdown ever attempted, at the speed of a slow walk, and to bounce and settle and report how the ground yields. This is the quiet part of planetary defence, and it does not photograph well. The dramatic moment was the impact, watched by millions. The useful moment is a small European spacecraft 4 years later, patiently measuring the weight of a thing nobody can see, so that the next time we have to hit something, we know what will happen. Kinetic impact is the only method that has ever been demonstrated. It is not the only method that has been designed, and for some asteroids it is exactly the wrong tool. If you have decades of warning, you do not need to hit anything. A spacecraft parked a few hundred meters off an asteroid pulls on it gravitationally, feebly but constantly. Fire your thrusters continuously to hold station, and the pair of you drift together, the spacecraft towing the asteroid by nothing but mutual attraction. This is the gravity tractor, proposed by the astronauts Edward Lu and Stanley Love in 2005. It requires no contact, no knowledge of the asteroid's strength, and no risk of fragmentation. It also produces an acceleration so small that moving a 300-meter body enough to matter takes years of continuous operation, which is why it belongs in the file marked Long Warning. The ion beam Shepherd is a cousin. Instead of using the spacecraft's own gravity, you point an ion thruster at the asteroid and let the stream of charged particles press against it, while a second thruster keeps the spacecraft from being blown backwards. The push is small, and it is steady, and it needs no landing. At the other end sits the nuclear option, which is not what the films depict. Detonating a device inside an asteroid would shatter it, and a shattered asteroid on a collision course is a shotgun blast rather than a bullet. The serious version is a standoff burst, some distance from the surface, where the flash of X-rays vaporizes a thin layer of rock on the near side. The vapor blows off, and the recoil shoves the asteroid. Nothing touches it. In 2024, researchers led by Nathan Moore at Sandia National Laboratories used a pulsed power machine to fire X-rays at small mock asteroids suspended in a vacuum, and watched them accelerate, the first laboratory demonstration of the mechanism. Nuclear deflection would be reserved for the cases where nothing else works, an object too large for a kinetic impactor, or one found too late for anything gentle. It carries political weight that has nothing to do with physics, since it means launching a nuclear device, and treaties and trust are involved. There is a final option that is not a deflection at all, and it is the one most likely to be used in your lifetime. If the object is small, tens of meters rather than hundreds, you do not move it. You get out of the way, you compute where and when it will arrive, and you evacuate, and you tell people to stay away from their windows. That has already happened, and it worked. On the 6th of October 2008, Richard Kowalski at the Catalina Sky Survey in Arizona found a very faint object. Within hours, the calculation showed it would strike the Earth. 19 hours later, a 4-meter rock exploded over the Nubian Desert in Sudan, exactly where and when predicted, and fragments were later collected from the sand. It was the first time an impact was forecast before it happened. It has since been done more than half a dozen times, each with a few hours of notice, each on an object too small to hurt anyone. 19 hours. That is what our current system delivers for the objects it can see. The trouble is the direction it cannot look. Every ground-based telescope on Earth is blind in the same place, and it is the most important place. An optical telescope finds an asteroid by the sunlight the asteroid reflects, and it must find that reflection against the background of the sky. Point the telescope near the sun, and the sky itself is blazing. During the day, the atmosphere scatters sunlight into a brilliant blue screen. At night, you're simply pointing away from the sun, at the objects that lie opposite it, which are the ones fully lit and easy to see. So the searchable sky is the night sky, and the night sky is the half of space away from the sun. Any asteroid that spends its time inside our orbit sunward of us appears from here in the same direction as daylight. It is there. It reflects light. We cannot see it, in the same way you cannot see a moth flying in front of a floodlight. Worse, an asteroid approaching Earth from the sunward side shows us its unlit face, the way the new moon shows us nothing. Even if it were in a dark sky, it would be nearly invisible. It brightens only at the last moment, when the geometry finally turns it toward the light, and by then it may be hours away. The Atens, the family that Apophis currently belongs to, live in exactly this region. Apophis was found in June of 2004 during a deliberate experiment to search closer to the Sun than surveys usually bother, which is why Tucker and Tholen and Bernardi were pointing where they were. Had they not tried it, we might have found this rock much later. The consequences are not theoretical. On the 15th of February 2013, an object roughly 20 meters across entered the atmosphere over the Ural Mountains. Nobody had seen it. Not one telescope, not one survey, not one alert. It came out of the dawn. On the 27th of December 2024, the Atlas telescope in Rio Hurtado, Chile, discovered an asteroid designated 2024 YR4. It had already passed the Earth. Its closest approach was 2 days before its discovery, and it had come in from the day side hidden by the glare, and had gone by us at about 828,000 kilometers before anyone knew it existed. 2 days. Had that rock been arriving rather than departing, the warning would have been negative. In July of 2019, an asteroid about 100 meters across passed within roughly 65,000 kilometers of the Earth, closer than a fifth of the way to the Moon, and was spotted a day or so before. Australian astronomers nicknamed it the City Killer. It arrived out of the same blind zone. The system we have built is superb at finding objects that come from the dark. It is close to useless against objects that come from the light, and the Earth, moving through space, sweeps up rocks from every direction without preference. What such a rock does when it arrives is not a matter for speculation. There is film of it. It was a Friday morning, 25 minutes past 9, in Chelyabinsk, a city of just over 1 million people on the eastern flank of the Ural Mountains. People were driving to work in the dark of a Russian February dawn, and a great many of them had dashboard cameras, because insurance fraud is common on Russian roads, and a camera is cheaper than a lawyer. So the arrival of the Chelyabinsk meteor is the best documented impact event in history, filmed from hundreds of angles by people who had no idea what they were looking at. The object was about 19 meters across, and weighed somewhere near 13,000 tons. It entered the atmosphere at 19 kilometers per second, at a shallow angle of about 18 degrees from horizontal, coming from the direction of the rising sun. For a few seconds it was brighter than the sun itself, casting hard, moving shadows across the snow. People stopped their cars, some got out. At an altitude of roughly 30 kilometers, the air ahead of it, compressed and heated to thousands of degrees, tore it apart. The rock did not explode chemically. It disintegrated under aerodynamic pressure and released its kinetic energy all at once, an airburst of about 440 kilotons of TNT equivalent, some 30 times the yield of the Hiroshima bomb. Then came the 2.5 minutes that mattered. The light arrived instantly. The shockwave took over 2 minutes to descend 30 kilometers to the ground. In that interval, thousands of people who had seen a flash walked to their windows and looked up and stood at the glass. When the blast wave hit, it blew in windows across 6 cities. Roughly 7,000 buildings were damaged. About 1,600 people were hurt badly enough to seek treatment, and the overwhelming majority of the injuries were lacerations from flying glass, and most of the injured had been facing the window. A zinc factory roof collapsed. Nobody died. Read that sequence again, because it contains the entire practical case for planetary defense at the small end. The rock did not hurt anyone. The windows did. And the reason people were at the windows was that they did not know what a flash in the sky meant, or that a shock wave was coming behind it, or that they had 2 minutes. An object of this size arrives somewhere on Earth roughly once every 50 to 100 years, and most of them come down over ocean or empty land, and are noticed only by infrasound sensors listening for nuclear tests. Chelyabinsk was the unlucky draw of a city. 20 meters is small. Apophis is 340. The energy scales with the mass, which scales with the cube of the size, so Apophis carries something like 5,000 times more energy than Chelyabinsk did. We did not see Chelyabinsk coming, and it was a rock the size of a house. There is a larger event in the record from a century earlier, and it fell in a place with no windows at all. Just after 7 in the morning on the 30th of June 1908, something exploded above the Podkamenaya Tunguska River in central Siberia. The nearest trading post, Vanavara, lay about 60 kilometers away. A man sitting on his porch there was thrown from his chair, and he described a sky that split in two, with fire filling the northern half, and heat on his face so fierce he thought his shirt was burning. Roughly 2,000 square kilometers of forest were flattened. 80 million trees went down, and the pattern in which they fell radiated outward from a central point, all pointing away from it like the spokes of a broken wheel. At the very centre, some trees remained standing, stripped of branches and bark because the blast came from directly overhead and pushed straight down. There is no crater. The scientist Leonid Kulik reached the site in 1927, 19 years later, and spent the rest of his life searching for the impact pit. He never found it, and the absence is the answer. The object never reached the ground. Like Chelyabinsk, only far larger, it was destroyed in the air, probably at an altitude between 5 and 10 kilometers, and its energy went into the atmosphere as a shock wave and a flash of heat. Estimates of the object's size have wandered over the decades and settled somewhere between 50 and 80 meters, with an energy somewhere in the range of 10 to 15 megatons. Whether it was a stony asteroid or a fragment of a comet is still argued. Tunguska is the size class that planetary defense actually worries about. A body large enough to level a metropolitan area, small enough that we have found only a tiny fraction of them, and common enough that one arrives every few centuries. Above that, the numbers thin out and the consequences do not. A body of about 140 meters, the threshold Congress wrote into law, could destroy a region. A kilometre-wide object would throw enough dust into the stratosphere to disrupt agriculture worldwide. And then there is the one that ended the argument about whether any of this matters. 66 million years ago, an object roughly 10 kilometres across struck the shallow sea off what is now the Yucatan Peninsula, at a place we call Chicxulub, after the town nearest its buried centre. It left a crater 180 kilometres wide, now covered by limestone and jungle. It threw molten rock across the hemisphere, set fires, and lofted enough sulphur and dust to darken the sky for years. Something like 3/4 of all species on Earth died, including every dinosaur that could not fly. That impact was not a catastrophe that happened to life, it was a hinge. Mammals inherited the world because a rock arrived on an ordinary spring day. The record is clear, and it is one-sided. The solar system has been throwing things at the Earth for 4.5 billion years, and it has never once stopped, and until 60 years ago no species on this planet had any idea it was happening. Now, a few hundred people watch the sky for a living. The system that watches is smaller than you would expect. It would fit comfortably into a mid-sized company. Most discoveries come from a handful of survey telescopes, running automatically every clear night. The Catalina Sky Survey operates from the mountains north of Tucson, Arizona, and has found more near-Earth objects than any other facility in history. Pan-STARRS sits on Haleakala in Hawaii, a wide-field telescope built to photograph the whole visible sky repeatedly. ATLAS, the Asteroid Terrestrial Impact Last Alert System, runs modest half-meter telescopes from Hawaii, Chile and South Africa, designed not to find distant asteroids, but to catch small ones in the last days before they arrive. Every position measurement from every one of them, and from hundreds of smaller observatories and thousands of amateurs, flows to a single place. The Minor Planet Center, hosted at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, has been the world's clearinghouse for small body observations since 1947. It runs on a staff of about a dozen. It receives hundreds of thousands of observations a day. From there, the data feeds two automated systems at the Jet Propulsion Laboratory's Center for Near-Earth Object Studies. Sentry continuously computes the impact probability of every known asteroid for the next 100 years and publishes a risk list that anyone can read. Scout does the same job for objects discovered in the last few hours, whose orbits are barely known at all, and it is Scout that catches the small ones on final approach. Europe runs a parallel system at its Near-Earth Object Coordination Center in Italy, deliberately independent so that the two can check each other. When something appears that matters, two international bodies exist to handle it. The International Asteroid Warning Network, established in 2013, coordinates the astronomers and issues the notices. The Space Mission Planning Advisory Group brings together the world's space agencies to decide what, if anything, could be flown. Both were created under the auspices of the United Nations, and both were, for a decade, entirely untested. That is the machinery. Telescopes that mostly run themselves, a clearinghouse with a dozen staff, 2 pieces of software and 2 committees. It cost a fraction of what one military aircraft costs. It has catalogued nearly 40,000 near-Earth objects, and it is the only thing standing between us and complete ignorance. For years, the people running it said patiently that the system had never faced a real event. Small impactors had been predicted, hours in advance, and they were rehearsals with no stakes. Nothing large had ever appeared on the risk list and stayed there long enough to force a decision. On the 27th of December 2024 in the Chilean Andes, an Atlas telescope photographed a moving dot near the limit of its sensitivity. It was catalogued as 2024 YR4, and it had already gone by. Closest approach had been on Christmas Day, at about 828,000 kilometres, and nobody had noticed, because the asteroid approached from the sunward side. The discovery came 2 days after the fact, as it receded into the night sky and became briefly visible. Being visible, it was tracked. The orbit calculation, run automatically, found that the asteroid would return to the vicinity of the Earth on the 22nd of December 2032, and that the Earth lay inside the uncertainty region. Everything that had happened to Apophis in 2004 happened again, 20 years later, to an audience that now included social media. The probability rose as the uncertainty region tightened around us. On the 27th of January 2025, the asteroid was rated 3 on the Torino scale, the second highest rating ever assigned, behind Apophis. 2 days later, the International Asteroid Warning Network issued a formal notice, the first time in its existence that it had done so. The Space Mission Planning Advisory Group convened. The probability peaked on the 18th of February 2025 at 3.1%, about 1 in 32. The size mattered. Ground telescopes measure reflected light, and a bright small rock and a dark large rock look identical. So the James Webb Space Telescope was pointed at it, because Webb sees infrared, and infrared measures the heat a body radiates, which depends on its actual surface area rather than its shininess. The answer came back between 53 and 67 meters, Tunguska class, large enough to destroy a city or to raise a serious tsunami if it fell in the sea. Then, as more observations extended the arc, the uncertainty region contracted past us, and the Earth fell outside it. By March of 2025, an Earth impact was excluded and the rating dropped to 0. The system had worked exactly as designed, in public, under pressure, for the first time. Except that the story did not end, because the Moon was also inside the uncertainty region. By the time the asteroid faded beyond the reach of even Webb, in June of 2025, the probability that it would strike the Moon on the 22nd of December 2032 had risen to about 4%, and it was still slowly rising as the object disappeared. It would not be visible again from Earth until 2028. That left a rock the size of a 15-story building with a 1 in 25 chance of hitting the Moon and a 7-year wait to find out. Andy Rivkin of the Johns Hopkins University Applied Physics Laboratory and Julian DeWitt of the Massachusetts Institute of Technology thought the wait was unnecessary. They applied for time on Webb, arguing that with new techniques the telescope could find an object reflecting about as much light as a single almond at the distance of the Moon. They observed on the 18th and the 26th of February, 2026. On the 5th of March, NASA announced the result. The asteroid will pass about 21,000 kilometers above the lunar surface. It will not hit. The relief in that announcement was mixed with something else, and the something else was disappointment. Consider what was lost. A 60-meter asteroid striking the Moon at about 14 kilometers per second would release the energy of roughly 6 million tons of TNT. It would excavate a crater somewhere near a kilometer across and 150 meters deep in perhaps 30 seconds. It would be, by a wide margin, the largest lunar impact ever witnessed by anyone. There was about an 86% chance it would have struck the near side, the face turned toward us. The impact flash would have been visible from Earth, plausibly to the naked eye, certainly through binoculars, and the best viewing would have been from Hawaii, with the western United States decently placed. Modelling by Patrick King at the Applied Physics Laboratory put the flash at a brightness that would have made it a news event of a peculiar and unprecedented kind. A date, a time, a place on a familiar face, and a light. Then the crater would have glowed in the infrared for hours as molten rock, heated to around 2000 Kelvin, radiated its heat into vacuum. Seismometers, if any were operating, would have recorded a moonquake of roughly magnitude 5. The Moon rings for a long time, having no water in its rocks to damp the vibration, and the wave would have told us about the interior structure beneath the impact, and debris. Most of the ejecta would have fallen back. But the Moon's escape velocity is low, and millions of kilograms of rock and dust would have left it entirely, and some fraction of that would have drifted into the space around the Earth over the following days and weeks. This is where the excitement acquired an edge. At a meeting of the American Geophysical Union in December of 2025, the NASA engineer Brent Barbee laid out the concern. There was perhaps a 1% chance, taking everything together, of an impact that scattered enough fine material into near-Earth space to matter, and near-Earth space is now crowded with satellites and with people. A millimeter grain moving at kilometers per second is a bullet. Nobody is certain how large the risk would have been. Nobody has ever had to find out. The other edge was time. Barbee pointed out that if a mission to the asteroid were wanted, it would need to begin development almost immediately, and that if Webb could not observe in February, decisions might have to be made in the face of real uncertainty. That is what the episode taught, and it is not a lesson about the Moon. Twice now, with Apophis and with this rock, the international system has watched a probability rise, held its nerve, gathered more data, and watched the probability collapse. Twice the collapse came from better observations rather than from anything anyone did to the asteroid. That is not a defense, it is a diagnosis. The system's response to a threat is to look harder until the threat proves to have been a measurement error. It works because most threats are measurement errors. The one that is not will not be dissolved by looking. What would actually help is seeing the objects earlier and seeing the ones we cannot see at all. On a mountain in northern Chile called Cerro Pachon, an 8.4-meter telescope with a 3.2 gigapixel camera, the largest digital camera ever built for astronomy, began releasing its first images in the middle of 2025. The Vera C. Rubin Observatory is not an asteroid mission. It is a survey machine designed to photograph the entire southern sky every few nights for 10 years, and to do so with a sensitivity and a cadence that nothing has approached. In its first 10 hours of test observations, it recorded more than 2,000 previously unknown asteroids. Over the course of its survey, it is expected to find millions of solar system objects and to multiply the catalogue of near-Earth asteroids several times over. It will also, and this matters more, follow objects long enough to determine their orbits properly, which is the difference between a discovery and a known thing. Rubin looks at the night sky. It cannot fix the sunward blind spot, and no ground telescope can. For that you must go to space and look in the infrared, because an asteroid glows with its own warmth, whether or not we can see its sunlit face. 2 missions are being built to do it. NASA's Near-Earth Object Surveyor carries a half-meter telescope with detectors tuned to thermal infrared, behind a sunshade 6 meters long that lets it point close to the sun without being blinded. It will sit at the first Lagrange point, 1.5 million kilometers sunward of Earth, and stare into the region the ground cannot search. Amy Mainzer leads the science. Jim Fanson manages the project at the Jet Propulsion Laboratory. Its 5-year baseline survey is designed to find 2/3 of the near-Earth objects larger than 140 meters. As of the middle of 2026, the spacecraft is in integration and testing, with launch set for no earlier than September of 2027 and no later than June of 2028. Congress first asked for this catalogue in 2005 and set a deadline of 2020. The mission that could deliver it was proposed 5 times and rejected 5 times, and starved of funding twice more after that. Europe is building NEOMEA, an infrared telescope, also bound for the first Lagrange point, aimed squarely at the objects hiding in the glare. Richard Moisel, who heads the agency's Planetary Defense Office, has noted that NEOMEA would have found 2024 YR4 about a month before the ground did, which would have given astronomers a longer arc and a faster answer, and Europe is deploying fly-eye telescopes whose optics split incoming light into 16 separate detectors in imitation of an insect's compound eye, giving an enormous field of view for automated nightly scanning. The first stands on Monte Mufara in Sicily. None of these instruments deflects anything. They do the only thing that has ever actually mattered, which is to convert an unknown into an object with a name and an orbit and a date. The question worth asking then is how much remains unknown. The honest answer comes in 3 parts, and only the first part is comfortable. Of the objects large enough to threaten civilization globally, those roughly a kilometre across and up, we believe we have found more than 95%. There are about 850 of them known. None is on a collision course with the Earth for as far ahead as we can calculate. This is a genuine finished achievement. The survey programs of the 1990s and 2000s set out to find these objects, and they found them, and the extinction-level threat, from asteroids at least, has been retired for the next several centuries. Of the objects large enough to destroy a region, from 140 meters upward, we have found something under half. Estimates put the total population near 25,000. We know of roughly 11 or 12,000, which means that somewhere out there, on orbits that cross ours, are more than 10,000 rocks, each capable of erasing a metropolitan area and its surroundings, and we do not know where any of them are. This is the population Congress asked NASA to catalogue by 2020, and the deadline passed, and the telescope built to meet it has not launched. Of the objects the size of the one that hit Chelyabinsk and the one that hit Tunguska, we have found a fraction of 1%. Nothing on any risk list today gives serious cause for concern. Sentry lists thousands of entries, and almost everyone has an impact probability smaller than the odds of your house being struck by lightning tomorrow, and the few that rise get resolved to 0 within months, as Apophis did, as 2024 YR4 did. So the quiet worry among the people who do this work is not about a specific rock. It is not panic. Ask any of them directly, and they will tell you, with some weariness, that no known asteroid threatens the Earth in this century. The worry is structural. It is that our warning time is set by our detection, not by our physics. It is that a Tunguska-sized object would probably arrive unannounced, out of the direction of the Sun, with the warning measured in hours or in nothing at all. It is that the deflection methods we have are slow, requiring years of lead time, and the detection system that would give us those years is not yet built. It is that we have run the fire drill twice and passed both times, and both times the fire turned out to have been a reflection. And underneath, there is the thing that they do not say in press releases, which is that the entire enterprise rests on a species-level accident of timing. For 4.5 billion years, the Earth was struck by objects it could not see and could not have moved. For about 60 years, we have been able to see them. For about 4, since a vending machine hit Dimorphos, we have been able to move them. That capability arrived in the last flicker of a very long story. It might have arrived after the rock instead of before, which brings us back to a Friday evening in April. Set the date in your mind again, the 13th of April 2029. By then, if the schedules hold, a European spacecraft will have been flying alongside Apophis for 2 months, mapping a grey, tumbling, two-lobed mountain of stone, having already answered questions that have stood open for 25 years. What it weighs, whether it is one rock or a heap of them, how the dust lies on its slopes, and on that evening the asteroid will come in from the sunward side, invisible, and swing beneath the Earth and rise into the sky over Europe and Africa. 2 billion people will be able to walk outside and look up. Some of them will. Most will not, because it will be a Friday evening, and there will be dinner to make, and the light will look like a star. The ones who do look will see a point of light moving steadily among the fixed ones. That is all. It will not be beautiful in the way a comet is beautiful. It will be ordinary and quiet, and it will take about an hour to cross the sky. While they watch, the Earth's gravity will be pulling harder on the near side of that rock than on its far side, and dust that has lain undisturbed since before there were oceans on this planet will begin, very slowly, to slide. Boulders will shift, the tumble will change, the asteroid will leave in a different orbit than it arrived in, no longer even a member of the same family, and a spacecraft will be there to measure every part of it, and another will be on its way. Nothing will happen to us. That sentence is the strangest thing in this whole story, because it was not always true. For a few days at the end of 2004, the number said 1 in 37, and it was climbing, and the people watching it go up did not know that a set of photographs taken 9 months earlier was sitting unexamined in an archive in Arizona. When Jeffrey Larson and Ann Descore went looking in those files and found a faint smudge exactly where the orbit predicted, the future changed. Not the asteroid's future, ours. The rock had never been coming. We had only failed to know. That is what all of this is. Not a shield, not yet, not really. Telescopes and archives, and a dozen people in Cambridge, and 2 pieces of software, and a few hundred astronomers who spend their nights measuring the positions of faint moving dots. What they produce is not safety. It is knowledge, arriving early enough to be useful. The universe has not become gentler. The same objects are on the same paths they were on when the trees fell at Tunguska, and when the windows broke in Chelyabinsk, and when the sky went dark over the Yucatan. What has changed is that a thin layer of glass and silicon and patience now sits between the dark and us, and it lets us see them coming, most of the time, from most directions, if someone has funded the telescope. On the 13th of April, 2029, a stone as long as a ship will pass beneath our satellites, and nobody will need to do anything about it because we looked. Sleep well,